for chemistry, day 62. The subject is density and buoyancy. So we're going to move away from intermolecular forces and states of matter. This is a subject that we'll cover. Density is a subject that's involved with what we're going to be doing next week, which is gas laws and solutions. Solutions being the mixture of a solute into a solvent and dissolving, for example, salt into water. So we're going to talk about density, and it answers the question, why does a large steel ship float while a nail sinks? So students answer this question by saying that the ship has air in it. This answer is partially correct, but it does not explain why the air makes the ship float. So there are two explanations for why some objects float and others sink in water, and one of these actually is several thousand years old. The Greek scientist Archimedes proposed the following explanation. An object will sink in water until it has displaced, that is, taken the place of, a weight or mass, we'll use the word mass in this unit, in this lesson, of water equal to the object's own weight. A second explanation was developed later. It's the density rule, and it's that an object that has less density than water will float, while an object that has greater density than water will sink. So we're going to examine those two rules. They sound like they're different. Let's see if they are. And the first thing we need to do is define what density is. So while these explanations sound different, they really are the same. First, let's define density. So density is the amount of mass that's put into a certain amount of space or volume. A plain way to state this is that density is how much matter, stuff, you've crowded into a certain amount of volume, space. If you look at a soccer ball and the steel ball below, they might both have the same mass, but the mass of the steel ball is packed into a much smaller amount of volume. So while both balls have the same mass or weight, and we're going to use the term mass in this assignment, but the mass of the steel ball is packed into a smaller volume, so the steel ball has greater density. The concept of density is defined around the properties of water, and specifically, water is defined, or density is defined as that 1 kilogram of water equals 1 liter of water. A kilogram is about 2.2 pounds, but we don't use pounds. So density is expressed as mass per unit volume, so the density of water is 1 kilogram per liter. So this states that 1 kilogram of water mass occupies a volume of 1 liter. This is not a coincidence. Density was defined this way in science. This means when you buy a 1 liter bottle of water at the store, it has a mass of 1 kilogram. So below we have water in a swimming pool. And then we replace 1 liter equals 1 kilogram of water with a wood block that has the same density. So let's look at these two examples below. So on the left, you have a swimming pool. It just has water in it, but we're going to carve out an imaginary block of that water, and we're going to call it our water block, and it's what's in that dashed line. So that volume, and it's in really, liters are in 3 dimensions. It's a 3-dimensional volume, but we have to use 2 dimensions here on the page. So that volume represents 1 liter, what's inside that dashed box. And since it's water, 1 liter is going to have a mass of 1 kilogram. So again, the density would be 1 kilogram per liter, mass per unit volume. So if you look at those arrows down below, that's water down below that imaginary box. They're pushing up with enough force to support 1 kilogram. They can't be pushing up with more force or less force, or otherwise that kilogram of water would be moving in one direction or the other. So they're pushing up with exactly enough force to support that 1 kilogram. That's called a balanced force. So the block of water is not moving either up or down. So let's read this down below. It says the arrows represent the water below the liter box that is holding the 1 liter of water in place. Since the liter box is not moving, the arrows must be pushing up with the same amount of force that the 1 liter, 1 kilogram box is pushing down due to gravity, and those are called balanced forces. Now, over on the right, what if we replaced the box of water with a wood block that was the exact density of water, that it also was 1 liter in volume, and it had a mass of 1 kilogram? The arrows below would not know, or would they care, if they are pushing up on water or wood. All the arrows know is that whatever is above the arrows has a mass of 1 kilogram and occupies 1 liter of volume. The situation in the diagram above means that a block that has the same density of water will sink until it exactly takes the place of the same mass and same volume of water. And this is what Archimedes said would happen. It also means that an object with the same density as water will sink until the top of the object just touches the top of the water, then it will stop sinking. So here are the rules for determining how far an object will sink. First of all, you determine the mass of the object. That's the first thing. Then number 2, you determine how many liters of water is equal to the mass of the object. In other words, the object's mass is going to displace that same mass of water. So what you do is you figure out how many liters of water that would be. For every 1 kilogram of mass, it's going to displace 1 liter of water. And then number 3, you place the object far enough down in the water so it takes up that many liters of water. So let's look at this example here. So we place the box on the left. So let's look at what that box is. It's 2 liters in volume. So let me actually explain what this is. This is just some imaginary sectors of 1 liter. And each of these dashed squares represents 1 liter. So everything down here is 1 liter. But once you get underwater, that 1 liter represents, because this is the water level, that 1 liter also represents 1 kilogram of water. Up above, this is air up here, so it's just 1 liter. Alright, so what we're going to do is we're going to take this box and we're going to place it in the water. So the box is 2 liters and it has a mass of 1 kilogram. So step number 1 says determine the mass of the object, and the mass is 1 kilogram. Then what it's going to do is it's going to take the place of 1 kilogram of water. So that would be 1 kilogram would be this one box right here. That means you're going to set the box down until the bottom of the box reaches right here. It's gone down and the 1 kilogram box has displaced 1 kilogram of water. But notice the box has 2 liters. So what happens to that other liter? Well, one of them takes up this space, and then the other one has to stick up above the water. So as this diagram over here shows, the box has a mass of 1 kilogram, so it sinks until it displaces 1 kilogram of water. This equals 1 liter of water. Since the box has a volume of 2 liters, 1 liter of the box has to stay up above the water. Okay, so there's the final image right there. Now, what's the density of this box? We know the density of water already is 1 kilogram per liter, so that's right there. That's the density of water. The density of the block is the mass divided by the volume. So it's 1 kilogram for 2 liters, or 1/2 kilogram per liter. So the density of the box, 1/2 kilogram per liter, is less than the density of water, which is 1 kilogram per liter. So 1 liter of the block sinks below the water because 1 kilogram of mass of the entire block displaces 1 kilogram of water. But since the block has 2 liters of volume, 1 of those liters sits up above the water. So we notice the other fact and the other definition, the density rule. So notice another fact. The density of the block is equal to the well, actually, let me get to this. That means since the density of the block is less than the density of water, it's going to float, at least partially going to float. Now let's get to this point. The density of the block is equal to the fraction of the block that is underwater. So you notice the density is 1/2, and you notice that 1/2 of the block is underwater. So as we continue to do some of these problems, let's see if that relationship continues to hold, that the density is going to equal to the fraction of the block that sits below the water. Okay, so now it's your turn. So we're going to do a series of these and just find out this relationship between density and whether an object floats or sinks or how high on the water it floats, okay? So let's go on to box number 2. And that has a volume of 2 liters and a mass of 2 kilograms. So rule number 1 says we determine the mass of the box, it's 2 kilograms. Then we identify how much water is 2 kilograms. Well, it's got to be, there's 1 kilogram and there's 2 kilograms. So it's going to sink down until it displaces these 2 blocks right there. It's going to sink down to that level. And then we have to determine, okay, there's 2 liters, so how much volume, or how much space is it occupying? Well, it is. It's already occupying 2 liters. So it sank down until it displaced 2 kilograms of water, and it already has a volume of water that's displaced of 2 liters, and therefore none of this box is going to stick up above the water. The entire 2-liter box is down below the water. So what's the density of that block? Well, it's 2 kilograms over 2 liters. But of course we can reduce that down, and it's 1 kilogram per liter. And you notice that that's the exact same density as water. And therefore it did the same thing as the very first box we talked about. It sank down until the top of the block just touches the top of the water. Okay, now the fraction of the block underwater is 1 over 1. Okay, and that 1 over 1 and 1 over 1 of the block is underwater. Okay, try to do these on your own before I do them, but I'm going to go ahead. You can pause the video. I'm just going to push ahead. So let's do the next one, box number 3. So that has a volume of 3 liters and a mass of 2 kilograms. So number 1, we determine the mass of the block. It's 2 kilograms. Number 2, we identify where is 2 kilograms of water. There's 1 right there, and there's 2 right there. So the block is going to sink down until it occupies these two blocks of water right there. Okay, so that's how far down the box will sink. Now we identify how much volume that is. 1 liter, 2 liters. But this block is 3 liters. So that has 1 more liter than this. So where does that liter go? It goes up above. And that's how the block would sit in the water. So the density of the block is 2 kilograms over 3 liters, or 2/3 kilogram per liter. That's the density. So you see that the density is less than 1. That's less than the density of water, so it is going to float. Now, what fraction of the block is below the water? Well, it has 3 liters, and 2 of them are below the water, so 2/3 of the block is below the water. So again, the fraction of the block that's below the water is equal to the density. Okay, let's move on to box or block. Sometimes I call it box, sometimes block. Let's move on to box number 4. And it has a volume of 3 liters and a mass of 1 kilogram. So go ahead and try to do this on your own. Pause the video. And if you pause the video, we're back. So 1 kilogram, so it's going to displace 1 kilogram of water. Well, where's 1 kilogram of water? It's just the very first block near the top, so it's going to take up that. Okay, and that 1 block of water is 1 liter. But this box is 3 liters. So what happens to the other 2 liters? They sit up above the water. And there's 3 liters and 1 kilogram. All right, so the density is 1 kilogram. Density of the block is 1 kilogram for every 3 liters, or 1/3 kilogram per liter. And what fraction of the block? Again, let's make the point that this is less than 1, so it's less than the density of water, so it is going to float. And what fraction of the block sits below the water? Well, there's 3 liters, and 1 of the 3 liters sits below the water, so 1/3 of the block sits below the water. And again, that fraction matches the density. Okay, try to do number 5. These are going pretty quickly. Again, just pause. Just take literally 30 seconds to do this. Okay, and we're back. And box number 5 is 4 liters and has a mass of 3 kilograms. So that means this block is going to take up 3 kilograms of water. So there's 1, 2, 3. And you don't have to assume that this is the bottom of the swimming pool. You can assume the swimming pool is deeper than this. Only so many boxes I can draw on the page. So it's going to take up 3 kilograms, so that's all 3 of these blocks down here. Okay, so 3 kilograms replace 3 kilograms of water, which is 3 liters of water, but the box has 4 liters, so it has 1 more liter than that, so that liter is going to have to sit up above. So density is 3 kilograms for 4 liters. And the fraction of the block underwater is 1, 2, 3 of the box is underwater and 1 on the top, so that's 3/4 of the box is underwater. Alright, so boxes 6 and 7 here, I'm going to leave those for you to do on your own. Hopefully this is not a real complicated concept for you and you can go ahead and complete those two in about 2 minutes, okay? So I'm going to move on to the next page, the last page here. It's going to be a different situation. Okay. So, box number 8 is a 1 liter box that has a mass of 2 kilograms. Okay, so we identify the mass of the block, and then we identify 2 kilograms of water. So 2 kilograms of water is going to be this first box and this second box. Okay, but there's a problem. Do you see what the problem is? This block is going to sink until it displaces a mass of water equal to its own mass. So it's going to sink until it displaces 2 kilograms of water. But 2 kilograms of water is 2 liters of volume. This block only has a volume of 1 liter. So it's impossible for this block to take up 2 liters. It can never take up 2 liters, and therefore it can never take the place of 2 kilograms of water. Therefore, we said it's going to sink until it displaces a weight of water equal to its own weight. It can never do that, simply because it's not big enough to do that. That means it's going to sink all the way to the bottom. So let's read this over here. So something happened here. The block is 2 kilograms and sinks until it displaces 2 kilograms of water, which equals 2 liters of water. But the block can never occupy 2 liters of water because its volume is only 1 liter. So the block will sink until the bottom. So what is the density of this block? Well, it's 2 kilograms for every 1 liter, 2 over 1. So there's the density. So that equals 2. 2 over 1 equals 2. That's more than the density of water. So it has a greater density than the density of water, and so it cannot, so it will therefore sink based on the density rule. So it can't ever abide by Archimedes' rule because it can never occupy 2 liters of water, and it does follow the density rule that if it has a mass or density, greater than the density of water, it will continue to sink. Let's just kind of look at what would happen here. So you put the block right here, because that block is only one liter. So you put it right here. Okay, so remember that this water right here is used to holding up 1 kilogram. Those arrows right there is the water right there where that dash line is used to holding up 1 kilogram. But all of a sudden you put 2 kilograms on it. So that's like giving a weightlifter too much weight, more weight than he can handle. It's just going to collapse. He's just going to drop it. He can't hold all that weight. So let's have it go down to here. We know that this, before you put the block in the water, these arrows, the second set of arrows I'm drawing, are used to supporting a weight of 2 kilograms. 1 kilogram here and another kilogram here. And all of those kilograms are pushing down here, so 2 kilograms. So this water right here can support 2 kilograms. So why doesn't the block stop there? Well, because the block is going to sink until it gets to here. And then that's 2 kilograms, and these arrows are used to pushing up on 2 kilograms of water. Here's the problem. This space doesn't stay empty. It doesn't just, there's not just nothing there. What happens is water rushes in from the sides and comes in here and creates another kilogram. So now you don't just have 2 kilograms pushing down on these 3 arrows. You now have 2. The block has 2, and then another 1 kilogram from the water that came in behind the block when it sank down to that level. So now you have 3 kilograms pushing down on water that's only used to holding up 2 kilograms, and of course it can't do that. That's too much weight for the weightlifter, so the block is going to continue to go down and down and down. Okay, so that explains why the block sinks. A little more complicated explanation than the blocks that float, but that obeys both Archimedes' rule and the density rule. Okay, so I'm going to leave this last one for you. It's going to ask you, does the block sink or float? And then the 2 on the previous page. If you have any questions, you can email them to me. And that would be that. So if I don't see you at the meeting tomorrow, I hope I do. You get 25 points of extra credit just for checking in and saying hi. Then I will talk to you then next week.